objects that are in free fall, they're all going to accelerate down towards the ground with the same acceleration, regardless of their weight. And if you don't believe me about this, then pause this for a second, grab something nearby, say a pencil and then maybe a big paperweight, and hold them up, drop them down, and you'll see they actually hit the ground at the same time. Now, this is not the case if you use something like a piece of paper that has a lot of surface area or something like that. This piece of paper is going to have air resistance that holds it backwards. And for the most part in this class, we're going to ignore friction or air resistance unless I say specifically, okay, consider friction, consider air resistance. But in general, all objects are going to accelerate downwards at the same rate, 9.8 meters per second squared. Now, if I were to think about my position, my velocity, and acceleration for an object starting from rest, I would write the velocity equation to look like that, and I would write the position equation to look like that. I would write the velocity equation to look like this. And again, I said starting from rest, so that guy is going to go to 0, that guy is going to go to 0, and that guy is going to go to 0. Now the reason I set this guy equal to 0 is because I said, hey, my initial position is going to be 0. Now it's going to accelerate downwards with an acceleration of 9.8 meters per second squared, and a ball that is falling is always going to accelerate at 9.8 meters per second squared. It's going to accelerate at that rate as soon as you drop it, a second later, 2 seconds later, and 3 seconds later. That's why I said a falling ball is a perfect example of constant acceleration. Now the velocity is simply equal to the acceleration times time. At 0 seconds, it's equal to 0. At 1 second, it's equal to 9.8. And you're probably looking at the negative signs right there. Remember, typically we define the positive y-axis to be up and the negative y-axis to be down. So my acceleration downwards is actually negative 9.8 meters per second squared based on the reference frame that we're defining here. 2 seconds, we can plug it into the same equation, and 4 seconds, you can kind of see that the velocity is increasing linearly with respect to time. If I were to plot my velocity as a function of time, it would look fairly linear. If I plotted my acceleration as a function of time, that is going to be a constant value over the entire flight. Now the position, that's going to be equal to 1/2 at squared, again paying attention to the quadratic, and you're looking at that right there, and first it's 4.9, that's 1/2 at squared, then 19.6, it's grown quite a bit more than the velocity has, and then 44.1, again growing much faster than the velocity, and that's because this guy is a quadratic, and it's going to increase something like that. It's going to look more like a parabola. Now, we can use these graphs like I drew in the last slide to make an analysis of linear motion. Now, we know that velocity is the change in position divided by the change in time, or x2 minus x1 divided by t2 minus t1. But if you think back to your algebra days, when you had an equation of y is equal to mx plus b, and you said, I can solve for m by doing my rise over my run, my x2 minus x1, how much I've risen, divided by my run. how far I've actually moved. You didn't think you'd actually use that again, but hey, you might. So you see that the slope looks like this when I'm plotting position against time. Position against time. And that looks a lot like the definition of my velocity. So if I'm looking at a plot of position versus time, then my velocity is simply the slope of that guy. So if my change in x is 11 meters and my change in t is 1 second, then my slope, my rise over my run, is equal to 11 meters divided by 1 second. That is also my velocity, 11 meters per second. Now, we can say the same thing about the acceleration being the change in velocity divided by the change in time. We can look at a graph of the velocity as a function of time, and we can say right here the velocity is increasing linearly with time. And what that means is there is going to be right here a constant acceleration. Now right here we're moving along with no change in velocity with respect to time. So there's going to be no acceleration. And right over here we're slowing down. That means the change in velocity with respect to time is going to be negative. So we're going to be slowing down, where we're going to have negative acceleration. And right over here we're going to have no acceleration. Now, when we look at the velocity being the change in position over time, we don't necessarily have to look at a curve that is linear, but as delta t approaches 0, then we're looking at slices that are smaller and smaller, and so we could consider delta v on these small intervals, where first we're looking at the run, and here we're looking at the rise, and then right here we're looking at the run, right here we're looking at the rise. We can calculate the instantaneous velocity at any given point as we choose our time intervals smaller and smaller. Now, I'm not going to spend any time on the summaries of these chapters. I'm just going to let you pause on them and make your own notes. Now, I'm not going to spend any time talking to these summary slides right here, but do feel free to pause on them and make notes on the important highlights from this chapter.